Welcome to MrCScience.com's video on how big is an atom. We're getting to the point where they talk about atoms and fun things like that, so we're going to use a couple concepts that you haven't been introduced to yet, but you will be shortly, and we're going to show you just how actually small an atom is. So what I'm going to do is I'm going to start with a block of copper. I have, whoops, wrong tool. I have a 1-inch cubed block of copper. It's all copper. That is a really horrid looking cube. There we go. Okay, that is copper. So what I did is I took the mass of that copper. So copper mass equals 147.2 grams. So, and that's 1 inch by 1 inch by 1 inch. If you're wondering about sizes, you can pull out a ruler and get a relative idea about the size of what that's going on. So 1 inch by 1 inch by 1 inch cube of copper has a mass of 147.2 grams. So let's look at copper on the periodic table of elements. It is element number 29, meaning it has 29 protons. Its atomic mass is 63.5. So I'm going to introduce a quick concept you're going to learn very shortly, is the mole. A mole is the atomic mass in grams. So 1 mole of copper is 63.5 grams. So from that, I want to see how many moles we have. How many of these units do we have in our 147.2 sample? I'm going to give us a little working room here. So we'll start with what I know, 147.2 grams, put that over 1, times, put what we want to get rid of on the bottom, grams, what we want to get, moles on top. So we know 1 mole is 63.5 grams. So we get out our calculator. Oops, ignore that. So let's take 147.2 and divide it by 63.5. And we get, sticking with significant figures, we get 2.32 moles of copper. Okay, now I did that so I can introduce another principle to you, or actually another term. It's called Avogadro's number. Guess who discovered it? Avogadro's number. What Avogadro discovered was that every mole has 6.02 times 10 to the 23rd atoms in it. So since we know our number of moles, we can figure out how many number of atoms we've got. So if we take our 6.02 times 10 to the 23rd, put that over 1, multiply that by what we want to get. We want to get atoms on top. We want to get rid of moles. And we know 1 mole has 6.02 times 10 to the 23rd atoms. Oh, this number right here is what we have. We have 2.32 moles of copper. So what we're going to do is basically take 2.32 times 6.02 times 10 to the 23rd. We'll talk a little bit about scientific notation here. So the first thing we're going to do is we're going to multiply the significant figures, 2.32 times 6.02. So we'll go back to our calculator. 2.32 times 6.02 equals 13.96, or going with 3 significant figures, 14.0. So we got 14.0 times 10. Now this is effectively 10 to the first. So 10 to the first times 10 to the, 10 to the 0, sorry. So 10 to the 0 times 10 to the 23rd. When you multiply exponents, you add them. So 23 plus 0 is 23. 10 to the 23rd atoms. Now this is in proper scientific notation. This decimal place should be here. So let's go 1.40 times, and since we are taking a 10 out, we got to add it on here. So times 10 to the 24th atoms in our 1 inch cubed, 1 cubic inch of copper. So that's how many atoms we got. Now, if we write that out, just to give you an idea here, we're not done yet. I'm going to try to make this a little more relative. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Add our commas in. So what do we got? Hundreds, thousands, millions, billions, trillions, quadrillions. I always forget what 5 is, hexillions. So we got 1.4 times 10 to the 24th atoms. Okay, so what does that mean? Here, I'm going to get rid of that. I don't need that. So, here, I can leave it. So that means it's a lot. It's a really big number. Most people can't comprehend it. So what we're going to do is we're going to pretend we got that many dollars. Imagine you have that many dollars. And then imagine that you could spend $1 million per second. How long would it take you to spend 1.4 times 10 to the 24th dollars if you spent 1 million per second? Okay, so first thing to do is take this 1.4 times 10 to the 24th and divide it by our 1 million. So we'll do 1.0 times 10 to the 6th. And that'll give us how many we can spend per second, how many seconds it would take. So 1.4 divided by 1 is 1.4 times 10. Now if you divide an exponent, 24 to 10 to the 24th divided by 10 to the 6th, you subtract them. So you get 24 minus 6, or 18 seconds. So it would take you that many seconds. Well, that still doesn't really tell us anything. So let's convert that. So if we put that over 1, I like the little circle there. Now let's go to hours. Now you know that there's 60 seconds in a minute and 60 minutes in an hour. 6 times 6 is 3,600, or we'll do 3.6 times 10 to the second seconds in 1 hour. So if we do this out, take our 1.4 divided by 3.6. 1.4 divided by 3.6 equals 0.38888. We'll just call it 0.3. Let's stick with 2 here. 39 hours. Oops, just a second. I forgot my 0.39 times 10 to the 18th hours. Again, we want to move that decimal place, so let's move that way. This time we have to pull a 10 off of there to do it. So 3.9 times 10 to the 17th hours. Okay, still a huge number, can't really relate to it. So let's work with those hours. We got 3.9 times 10 to the 17th hours. Let's turn those hours into days. Let's see. Day on the top, that's what we want to get. Hours on the bottom. We know 1 day is 24 hours. So if we take this number divided by 24, so let's go our 3.9 divided by 24 equals 0.16. So equals 0.16. Oops. There's a decimal place there. Times 10 to the 17th days. Again, let's move that decimal place. We have to pull a 10 out of there, so we got 1.6 times 10 to the 16th days. Now that still is a big number, so let's convert it to years. 1.6 times 10 to the 16th days over 1 times, we know that, let's go to years, days. We know that 1 year is 365 days. So if we take our 1 point here, let's clear that. We're kind of going with significant figures. We're not as accurate, but the significant figures we'll work through. 0.16 divided by 365 equals, okay, 0.4 or 4.4 times 10 to the negative fourth, or we could write that as 0.0, oops, 344 times 10 to the 16th days, or years. We're going to move that decimal place 1, 2, 3, 4 places to 4.4. Doing it to 4 places, we have to pull 4 out of there, times 10 to the 12th years. Now that's getting smaller. Let's go ahead and write that out. So if we do 4, then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We got our decimal places, so we got our millions, yeah, millions, billions, quadrillions. We got a little over 4 quadrillion years to spend that money. So that can give you an idea of just how many atoms there were. So if we were to remove 1 million atoms from that per second, it would take us over 4 quadrillion years to do that. So that gives you an idea of how big the atom is. If you have any questions on that, feel free to drop me a line at mrc@mrcscience.com.